Thank you very much. So I would like to thank the organizers for allowing me to speak, and also for organizing this very nice workshop and long program, an extended program. So this talk has a very long title. I hope that the talk will not be long. So so I will try to. Let me just briefly say that. So exactly the point is to try to compactify this set of sequences of positive real numbers, and then we will see. We will try to basically capture all these asymptotic behaviors, and then we will see how we can apply this to graph limits and to other things. This is a joint work with David Hudonsky, who is in Prague, in the Czech Academy of Sciences. And yes, so let's begin. So this is the summary of the talk. So I mean, if you get that slide, that's it. So the plan is, so I have just put these as all these journalist questions, right? I mean, what, why, when, where, how, who, yeah? So basically, why we are interested in this kind of thing. So what's the motivation? The motivation is graph limits, limits of graphs. I will motivate why we are interested in limits of graphs, but so that's our motivation. So what are the results and some of the immediate implications of that motivation? So that's what and how we do that. So the aim is to bridge the gap between the dense limit, the notion of limits of graph sequences for dense graphs, and so also for sparse graphs. So that's the goal, and so that's why we do it. Then we'll do a historical intermezzo. So this will explain who was involved in these kind of things, where, and also when that happened. And finally, we will see some other applications of the results to other sequences, for instances, to completely monotone functions, and some special functions, and also some applications to random graphs. So that's kind of the aim of the talk. Okay. So let's begin with the motivation. So we are interested in graph limits. And what is the aim of graph limits? So basically, or at least that's how I like to see it, it's you want to summarize somehow the information of a big network. And so what do? You kind of look at how somehow this evolves, and how you kind of give a limit of this sequence of objects, and then you try to study such a limit. And then what's the idea? The idea is that the least limit somehow will give you some information of the finite networks. And so the thing is that depending on what information you want to summarize, you extract a notion of limit. And for instance, and then this notion of limit, then you can talk about when a sequence of graphs is convergent and when it's not. So one initial motivation for that, or one good notion for that, is the result by Lovas, which says that if you have a finite graph, this is exactly the same information as if you give the number of homomorphisms from a graph H to G. Okay, so if you have a finite graph G, then this gives you exactly the same information as if you would have all this number of homomorphisms. So you compute all this number of homomorphisms, for instance, for an H to G, for a triangle to G, and all possible finite graphs. And then if you have this infinite amount of information, then you precisely have exactly the same information as for a finite graph G. So this is a result from the 60s. And then this motivates, because basically if you have your finite graph, I mean if you have this collection of numbers, then you have the finite graph, then this motivates the notion of limit. So what do? You are interested in the number of homomorphisms, but of course you should allow some leeway. So you allow some blow-ups from these vertices, and then from this you jump to what is the probability of a random map being a graph homomorphism, okay? And then once you have that, this creates the notion of left convergence. So namely, for each finite graph, you look at the sequence of probabilities that a mapping peaking uniformly is a graph homomorphism. And then you want that all these probabilities converge for every finite graph. So again, so this is the definition of left convergence from Borges, Chase, Lovas, Schoch, and Bernstein-Gombi. So you have a sequence of graphs. You say that is left convergence if for every finite graph H, there exists some constant between 0 and 1, both included, such that when you look at the number of homomorphisms from H to G, so what is an homomorphism? Graph homomorphism, recall that is a map from the vertices of F, from the vertices of H to the vertices of GI. such that it preserves the edges. So it sends edges to edges. And then you normalize by the total number of maps that you can have. So this is exactly the total number of maps that you can have. And if you have that such a limit converges to C of H, so this constant depends on the small graph H, and you have that this limit converges for every H, for every finite graph H, then the sequence is convergent. So and out of that, like Lobas and other people, they develop all the theory of these graph-ons. Yeah? So this is the notion of the limit notion that they use. Okay, so what is one of the features or one of the inconveniences or one of the things that happen is that when you have a sparse graphs, so when you have a sequence of sparse graphs, namely that you have little o of the number of little o of the number of edges of a complete graph, so that your number of edges is little o of that, then all the possible probabilities, they trivialize to 0, right? I mean, you have no chance of finding any graph, any finite graph with positive probability. So you basically have the 0 graphon. So basically every possible sequence of a sparse graphs trivializes to the 0 graphon. So that's something that happens. And then what happens is that, okay, so I'm interested in finding some notions of limits for sparse sequences. So then you have to come up with some other notion that try to capture these sparse regimes, right? There are many notions, but most notably, one that is fairly famous is the Benjamin-Isham convergence, which deals with the case that you have very sparse graphs. Namely, graphs that have maximum bounded degree. So you take a bound, as large as you want, delta, sorry, and then you consider a sequence of graphs which have all the maximum degree bounded by this gamma. It doesn't have to be regular, it can be like just the trees or whatever, but the maximum degree has to be bounded by gamma. And then what do? Then you look at, okay, so you will look at every vertex, and then you will see how is the neighborhood of that vertex look like. And because you have bounded degree, the number of chances that you have up to a certain distance r is finite. So you can basically just say, okay, how many copies do I have that look like this graph? When you root a vertex, so you root the graph, sorry, you root a graph, and then you look at a ball of radius r out of that root, then you go along the graph, you put the root there, and then you look if your induced graph is that one. And then if you do, I mean, you compute how many vertices look like that. And then if all these possibilities converge for every root, sorry, for every radius, and for every graph that has that is rooted at a vertex and has this maximum radius, then you say that this sequence converges. Okay, so that's good. That's very nice. And then alternatively, what you can do is you can do an observation. It's like, okay, so if instead of like looking at this induced graph homomorphisms, instead I just look at the number of graph homomorphisms, you can see that indeed by doing an inclusion-exclusion argument, the convergence in Benjamin-Isham sense is exactly equivalent to say that this number, so once you have a sequence of maximum bounded degree graphs, then the notion is exactly the same as if you ask that the limit of this number of homomorphisms from H to Gi, when you normalize by the number of vertices, they converge to a different constant, CH, for every finite graph H. So instead of looking at the induced graphs, you now look at just the number of graph homomorphisms, and then you do an inclusion-exclusion, and then you see that you have a conversion in this notion if and only if you have a conversion in Benjamin-Isham sense. So that's perfect. And then you observe here, and you are like, okay, so what? Let me go back. So here, you are counting number of homomorphisms, and then you are dividing by one function. Then you go forward, and you're like, I'm looking at the number of homomorphisms, and I'm dividing by another function. So what happens is that, of course, you are looking at different regimes, so then you divide by different functions. And then you're like, okay, that's interesting. Okay, so let's keep that in mind. Then let's try to summarize a bit all these two notions, and let's try to compare what sort of results we have for these. So both notions, as we have seen, they involve counting small subgraphs, so counting the homomorphisms of small graphs into a big graph for all possible small graphs or finite graphs. And then they have nice, but they have different limit objects, okay? So for the left conversions, you have the graphons, which are measurable functions from 0, 1 squared to 0, 1, which are symmetric. And that they have also, you should mod out by measurable permutations of the coordinates. Why? Because you are, in your graph, you are interested in graphs up to isomorphism. Hence, you can permute the labels of the vertices. So this is exactly what this measurable permutation of the coordinates does. So you have to think of W as basically a beef-up version of the adjacency matrix. And so there is this question of realization, and it's namely, okay, so now if you have a limit sequence, if you have a W that is like that, is there a sequence of graphs that actually has as a limit that graphon? And the answer is yes. Every such thing has a sequence of graphs that converge to that. Wait, sorry. And this is the realizable question that is completely solved in this case. Then in the case of Benjamin-Ishram, the question is slightly more tricky. And there is these objects called graphings, which basically you have a probability space, and you ask for the edges are picked from a Broad set in the product sigma algebra. And then they have to satisfy the mass transport principle, because you want to count the number of edges from one vertex to the next. So from one vertex set to the other is exactly the same counting both ways, right? So you want to have this double counting. So the edges from A to B has to be the same as the edges from B to A. So this is exactly what this mass transport principle does. And then also you have that at each point it has bounded degree, because of, recall that that was the condition that we had for when considering sequences of graphs, that we had this degree bounded. But then the problem is that the realizable question is not fully understood. So what does it mean? That if I have one of such objects, it's kind of hard to determine whether there will be a conversion graph sequence that will have as a limit that graphing. So it is not known. There are some that you know that they are. There are some that you know that you cannot reach, but it's not clear. And so there is one feature in both cases that is kind of, for me, I think it's really relevant, that is the following. In both cases, for every sequence of allowable graphs, namely that bounded degree or any sequence in the case of left conversions, every sequence has a conversion subsequence, okay? In both notions, this is the case. So once you have a sequence, maybe the sequence itself is not convergent, that's fine. But then there will be a subsequence that is convergent. Why? Because basically these are all compact things. And I mean, when you are looking, well, if you think about it, like everything is kind of compactish or finite or things like this. So you will always be able to do some diagonal argument and reach some conversion subsequence. So this, I call it compactness. So we are interested in that feature. Okay, so keep that in mind. Okay, so basically, we are interested in this compactness, and we are interested in something. I mean, we kind of guess, counting small subgraphs is interesting, and also we want to preserve this kind of compactness thing. Okay. So, as we said, in both cases, we are counting these graphomorphisms, and so, in some sense, we are trying to capture its growth rate, right? In some sense, in the first case, we were dividing by the total number, and then we said, well, if that converges to 0, then, well, I kill it. Okay, fine. But if not, then I have it grows to some constant, good. And in the other case, because they grow as the number of vertices, then I normalize by that. So in some sense, you are trying to capture the growth rate of such values. So let's try to do that. Okay, let's go and take us like going from a hammer perspective, you know. Let's go like very, very hammer-like. And let's do the following. Okay. So imagine that you take two sequences of positive real numbers. And so these omega will stand for, you can think of these as the natural numbers. Yeah, it's the same. And then, but just, I mean, it's kind of, at some point you get used to this. And then you consider the following partial ordering. So you say that two sequences are ordered, and they are one strictly smaller than the other, even only if the limit of the larger one divided by the smaller one goes to 0. yeah? Or the smaller one divided by the larger one, sorry, goes to 0. I mean, the other way around would go to infinity, right? Okay, and then you say that they are equivalent if up to a constant, that now it cannot be either 0 or infinity, right? So it cannot be 0, let's say. Infinity, it's not a constant. Sorry. It cannot be a constant. It's not a constant. Then you have that this ratio is actually a constant.
But the limit has to exist.
Yeah, the limit has to exist, exactly. The limit has to exist. So what do we don't want? So why this is a partial order? Well, because you can have, oscillation behavior, right? So you can have a function like this, and then you can have like, go like this. And then this, of course, these two sequences will not be comparable, right? So it's a partial order. So we are only interested in things that can be comparable or things that cannot be comparable, but we want to understand this. Okay, so now, with this partial order, let's take a totally ordered subset that you can compare every two sequences. Why? Because it's kind of nice. Then you can kind of say, oh, this is larger than this one, and so on. So it's nice. And then imagine, for the sake of it, that you contain all possible integer powers n to the I, right? All of these sequences are convergent, all these polynomials are convergent, all are comparable, so you just put them, and then you just take a maximal out of it, so you just keep filling it until you cannot add more. And then consider that set A, and then you say, you define this in the following notion, which we call it Q convergence, but you can call it something else, as you prefer. Then you say, okay, so let me give a sequence of graphs, and with a caveat, and this is kind of important, let's add an extra loop at each vertex. Why? Because we don't like zeros. Okay? So if you add the extra loop at this vertex, then every possible graph will have some graphomorphism, because you can collapse everything, and then poof, because there is the loop. You can never have any graph cannot have zero homomorphisms to a graph that has some loops. So you just add some. That's kind of to normalize the thing, but it's not a big deal, but it's keep in mind, because remember that here, yeah, we want strict larger than 0, okay? Good. Yeah, you don't want to divide by 0, right? So you do that. Okay, and then what you do, you say, this sequence Q converges to now a function, comma, a constant for every finite graph H. If there is a constant between 0 and infinity, so a strictly positive real number, and some function in this set A, such that the growth rate of the number of homomorphisms is captured by this function. So you'd say, oh, I have a quadratically number of triangles. Okay, so if you have your function is n squared, boom, voila. Then it would converge to that, this number. Yeah, to some, let's say, 2 times n squared, okay, then that number will be 2. Yeah? Okay, and so you observe that what you do is here, you are dividing by the number of vertices there. Yeah? So it's a function of the number of vertices. So this is you are trying to capture both regimes. Yeah? And so actually, if you do that, it's like, okay, yeah, actually this generalizes the Benjamin-Ishram sense, convergence, and the left convergence. Yeah? Why? Well, because for the Benjamin-Ishram, you only put linear functions. And for the left convergence, you put n-squared functions. I mean, polynomial functions, right? Because all these functions, f of h, they grow as polynomials. Yeah? Number of degrees of 1 to the power of the number of degrees of the number of vertices of h. Okay. Also, if A is maximal totally ordered set, such a maximal totally ordered set, it exists. Why? Because you can use, well, we are assuming here that we have the axiom of choice, or Hausdorff maximal principle, or Zohn's lemma. So you just keep filling it, and then until you cannot reach, and then you have a set A that is maximal totally ordered set with that order. Okay, that's nice. But the question is, what is contained in A? Yeah? What if you have some growth rate and A doesn't capture that? Well, that can happen because, it's a maximal totally ordered set. What happens? So the question is, can A capture every possible growth rate, right? In some sense, right? Of course, you can always, you have these, and then, I mean, you can have, pretty well, but in some sense, can you have a nice set A that captures every possible growth rate, in some sense? And what about a limit object? Yeah, I don't know. Okay, so let's aim for the red. So this is the theorem that we have with David, and is that actually, assuming the continuum hypothesis, there exists such nice set A. Namely, assuming the continuum hypothesis, there exists a totally ordered set with that order that we have set of sequences of positive real numbers in such a way that if you take a subsequence of some of your favorite sequence, then there will exist a function in your set A. There will exist a subsequence of your subsequence. So you have a subsequence, and then there will exist a subsequence. And there will exist a constant between 0 and infinity, such that this is the subsequence, such that when you do the limit along that subsequence, the ratio is constant, is that constant that you have selected C. So what does it mean? It means that, in some sense, this set A is such that no matter how you give your sequence, there will exist, along a subsequence, there will exist a sequence of your set A that it will be comparable to that, along a multiplicative constant. So in some sense, it says that every conversion has a partial conversion. Every sequence has a partial conversion subsequence, in some sense. But here we are talking about things that grow. Yeah? And the important part here is that A is a maximal totally ordered set. Of course, it has to be maximal because otherwise you would not be able to capture all possible things, right? But actually, you can have such a set that captures all this growth in this subsequence behavior. Okay, so that's good. So, so in some sense, A is, in some sense, is the densest possible case because you are capturing all possible asymptotic growth. A, the interesting part is that has some set of comparable test functions. So in particular, what you can do is you can start to compare sequences of graphs that have, say, even number of vertices with a sequence that has odd number of vertices. And why this is interesting? Because one possible option of actually do this compactification argument is actually using some ultrafilters. But then if you do that, you are kind of using the ultrafilter properties to sort of help you with the limits. And that's something that if you want to compare things that are in a disjoint set of indices, that you cannot. Yeah? So that's why we are interested that's why we find this external set of functions that actually carries you and allows you to say they are comparable, even though they are not on the same index set. And so, for instance, some extensions that actually we use is that if instead of all possible set of sequences, you are only restricting to some sequences that actually grow in between two functions, say, for instance, between I and I squared, or between two polynomials, or between the polynomial and exponential, you only take these ones, you don't have the whole set of sequences. You can actually take a maximal totally ordered set that has these nice properties that we said, and that actually these upper and lower functions belong to your set. Right? If they are comparable, if they are pairwise comparable, so this is why you need, this is why you need this search of condition here. That this means basically that they are nice, comparable, then you can actually do that. And also, for instance, if you have a nice set of that you might be interested in, and that is totally ordered, for instance, all the possible polynomials n to the alpha, then you can also include that in your set and increase that. So you can have the set A can have some nice properties of containing some subsets that you might be interested in. Okay. So how do we prove that? Well, we use a transfinite induction. And where does the continuum hypothesis comes into play? It's because there are continuumly many infinite subsequences. So we use the continuum hypothesis to put them, to biject them with omega-1. And then we use a transfinite induction. So we just keep going. And so what do we do? When you have a normal ordinal, a normal ordinal or a sequential ordinal, so from A alpha to A alpha plus 1, if your new sequence of your new subsequence actually agrees up to a constant C with something that you have previously found, then you don't do anything because you have already captured that growth rate. And then otherwise what you do, because you have up until that point find only countably many, then you start to say, okay, so I will compare my sequence with these countably many ones, and then if I cannot, I will basically create a cut of the upper ones and the lower ones by just taking a subsequence of that, of my subsequence that I had, such that this subsequence will go basically in the middle and will separate the things. And then once you have them separated, you just complete it, and then that's your new candidate. And you keep doing that, and then what do you do? For the limit ordinal, you do the standard thing of you just take the union up to that point. For a limit ordinal, so this is for a normal ordinal that you have the next one, and then for the limit ordinal, you just take the union. And that's how you construct the set. Good. So what do you do now with this? You basically use a diagonal argument and say, okay, so now because I have only countably many graphs, then what do? You begin with the first one, and then you say, okay, what's my growth rate? And then I know that up to a subsequence, I will capture it. Then when you have this subsequence, then you take the next growth rate, the next graph, and you go along a subsequence capturing its growth rate of that subsequence. And then you do the subsequence of that subsequence, and so on and so forth. And then you go along the diagonal, and then you basically find a subsequence that converges to every, you find a subsequence such that converges to f of h up to this constant ch for every h, for every finite graph. So you do a standard diagonal argument. And that's why we can show that in this notion, you have this compactness property, that every sequence has a conversion subsequence in this Q-conversion notion. Good. Okay? So future work is to find a limit object for this co-conversion notion, or weaken this the continuum hypothesis that we have used, which ask David. Okay, so I don't like that's his business. He's an expert in set theory, so that's why. Okay, good. So now time for historical intermezzo. So this for this part, there is a very interesting article of Philip Ehrlich, who is now retired, I think, but he's still, it's emeritus now. It's called the Absolute Arithmetic Continuum and the Unification of All Numbers Great and Small. It's a paper on history of maths, and explains a bit all the history of this continuum hypothesis, and in particular, it explains kind of where all this came from. So the history of this begins with in Germany, actually. So with Dubois-Reymond in the 1887, he was the first to consider this sort of partial order. This partial order that you compare them by the quotient. And what was he interested in? He was actually interested in finding, so at that time people were wondering for criteria for summability of series, right? And so what he was, so there were many criteria, and there was a sequence of criteria. There is a sequence of criteria which kind of it's stronger and stronger. And what he wanted to find is, okay, so let's try to find with this ordering of sequences, let me try to find something that is strictly in the middle of a convergent sequence and of a summable sequence and a non-summable one. So that's what he had in mind, because he wanted to understand this separation between summable and non-summable. So he wanted to find what he called a pentakey of sequences, had essentially no holes. Yeah, so it was maximal. And so he proved, for instance, that for every sequence of functions, you have something. You have always for every countable sequence of functions, you had always one that grow faster than all of them. Okay. And so Cantor criticized actually this work because he said that it was not rigorous. Well, because he was aiming to try something that didn't exist, right? Something that was something is either summable or not summable, right? I mean, we are talking about sequences of positive real numbers. So then he's like, well, what are you doing? You know? But well, some other people work on this, in particular Hausdorff in the 1900s. And so what he did is he changed the relation of divisibility by the difference, and actually he considered as well this set 0, 1 to the omega modulo fin. What does modulo fin means? It means that you are considering that one sequence is strictly smaller than the other if eventually one is always strictly smaller than the other. So one has always 1, so if it has a 1, then the other one can have 1 or 0, but if one has 0, the larger one has 0, the lower one has to be 0 as well. And this is from some point on. So this is what modulo final, right? And so Hausdorff actually in all these works, is where he introduced this Hausdorff maximal principle that we talk about, that is equivalent to the axiom of choice. And that's where he showed that actually that's what, for him, what was a pentakey, right? The maximal thing that you cannot add more. And so what he found is that, well, he showed that there are no omega-1, no omega-omega gaps. What does it mean? It means that here you have a sequence of increasing functions, exactly, and here a sequence of decreasing functions. Each of these is larger or equal than each of these. And so then the question is whether you can put something in the middle. And actually the answer is yes. If you have countably many here and countably many here, you can always put something in the middle. But also, and this is important, he constructs what has been called a Hausdorff gap, which is a omega-1 gap. So if you do this, but instead of here just countably many, you put omega-1 many, and here you put omega-1 many, actually there are some occasions in which you cannot find anything in the middle. And so he first gave these using a cardinality argument, assuming the continuum hypothesis, but actually he got rid of this continuum hypothesis, and actually find a Hausdorff gap without the continuum hypothesis, which was really achievement, and many people has worked in that thing since then. And then Hardy in the 1910s, he said, okay, well, I like this notion very much, but I like to consider nice set of functions, so he considered scales of growth, right, so to try to compare them. And so he considered specifically logarithmic exponential functions, which are nice functions. So basically, you have polynomial, rational functions, exponentials, and logarithms, and you can iterate that. I mean, you can compose them, and you can sum them and stuff like that. So this actually creates a field of germs of functions, because germs of function, why? Because you are considering that two of them are the same if they are from some point on the same. So you really, at the beginning, you know, if they do some weird things, like, well, the logarithm, you know, at 0, it goes to 0, but it's not a big deal, you know, eventually it's okay. So that's why he considers, like, from some point on. So that's why he calls germs of functions. And so he introduced what later became known to Hardy fields, which are these fields of germs of functions that are infinitely differentiable. And so they are exactly the field of functions that are closed by differentiation. And you consider these fields of, so these germs, you've considered them at infinity. So it's from some point on, right? From some point on, they have to be the same. They have to be well-defined and so on and so forth. So for instance, you have logarithm of, you know, like x minus 14. Well, that's also allowable because, you know, eventually it's well-defined. Okay, good. So after that, so how I can apply or result to some other things that people were interested in. What we can do, for instance, if in this set of, in this set A, what we can do is that if we have a very nice set of sequences or very nice set of functions, in particular, if you have a set that is separable, namely that you have a countable dense subset, sorry, then what you can ask is that your set is included in this maximal set A. Okay, so if you have a nice set C, for instance, this n to the alpha, right? N to the alpha real, you have these rational many quotients, and actually that acts as this dense set. So you can ask for this C to be in your set A, but you can ask for some other stuff. So, for instance, for completely monotone functions. So what are completely monotone functions? So completely monotone functions are very nice functions that basically don't oscillate. Okay, so how they are defined? So they are defined as going from positive reals to positive reals, actually. That, so you can, at every point x larger than 0, the derivative, its nth derivative is defined, and actually it has this property. So it oscillates. So what does it mean? It means that, so if you take n equals 0, so this means that the function is positive. But for n equals 1, it means that the function that the first derivative is negative, so it decreases. But then the second derivative is positive, so it means that the decreasing decreases. And then the decreasing of the decretion decreases. So it's kind of compensated. So somehow it never oscillates. So for instance, what kind of functions you have there? Well, 1 over exponentials, 1 over logarithms, 1 over polynomials, things like this. So very nice functions that really don't oscillate, and they go to 0. Or alternatively, if you prefer, you can just take the first derivative and then you just basically make them, but they are increasing instead, and they are positive and increasing, or things like this. So you can play with these a tiny bit. They are called Bernstein functions, but whatever. I mean, they are basically the same, or very related. So in the beginning of the 20th century, there is this theorem by Hausdorff. It's called Hausdorff-Bernstein-Weider, or that you can find it in a very nice book, The Laplace Transform. Well, or better, no, you can find it in many places, but there is a very nice book written by Weider in the 1950s, which is called The Laplace Transform. And basically, what this theorem says is that using the Laplace transform, there is a correspondence between positive measures in 0, 1. Actually, this is the Hausdorff problem. This is the Hausdorff moment problem, and completely monotone functions. So there is a one-to-one correspondence, and this is basically the Laplace transform, and that's exactly how you will work it out. So there is exactly using the Laplace transform, you can go from a set of positive measures to a set of completely monotone functions. That's really nice. And then what you can do with that? Well, the thing is that these completely monotone functions, the ones that go the fastest to 0 are the 1 over the exponentials. So they are exponentials with a coefficient, an exponent, a base between 0 and 1. And then what you can do is like, okay, so imagine now that you have a set of sequences or a set of functions that they are like this. So they decrease, but that they decrease in a less fast way than any exponential. Exactly, they decrease in a less fast way than any exponential. So we call it supra-exponential asymptotic decrease, yeah, because they decrease slower than any exponential. So for instance, 1 over a polynomial, 1 over a logarithm, things like this. And then what you can do, using a very nice result by Rosenblum from the 50s, and actually this from the 70s, 80s, kind of a summary. These two are in French, and this one is a summary in English. It's kind of, of the result. What you can do is like, you can actually, if now you have this set of sequences, now you choose sequences that go to 0, but that go to 0 a bit in a less fast way than any exponential function. Okay, so this is exactly what it means. Then, what you can actually capture all these possible growth rates by a set of maximal totally ordered set that actually is full of these very nice non-oscillating functions, full of these completely monotone functions. Okay? So basically, so you can have something that goes to 0. For instance, here you can go to 0 like this. But then you can take a set A that it's of totally completely monotone sequences, so they are very nicely go to 0 without oscillating, that will actually capture this growth along a subsequence. So in particular, you can actually, if you go back, you can actually go and find a positive measure on 0, 1 that corresponds to that, in particular, to this growth rate. And these sets that I'm mentioning are completely, totally ordered with the order that we said before. Good. Okay. And finally, and this is, good. So finally, using a result by Jansson, Oleskiewicz, and Rudzinski, or two results from the 90s and the 2000s, what we can say is like, okay, so now imagine that you have a sequence of random graphs, G and P. Okay? And then the question is, okay, so now you have this convergent sequence. This notion of co-convergence is like, okay, so you have a sequence of random graphs. Does it converges? Absolutely, almost surely, or what happens with the sequence of random graphs? I mean, you gave me this sequence, I mean, what happens with the G and Ps? Well, actually they converge to what they are supposed to converge. And what do I mean by that? So I want to be clear here. So what you do is like you take a sequence of GNPs. You take for some Pn, some probability function that is non-zero. Yeah? But it can go to 0, yeah? That's not a problem. And then, and then what you do is like this L here means that you have added a loop to each vertex. Okay? And then what you compute is that the number of homomorphisms from every finite graph to this thing in which you have your GNP, and poof, you put a loop at each vertex. And this is important, because then you have no, I mean, there is always triangles. There is always K4s. There is always anything for every probability. So you are never dividing by 0. Okay? So there is always something, right? Because you are counting these homomorphisms. And then you have an expected number of homomorphisms, which is this one. And then what you do is like you say, okay, so now give me just a list of as many graphs, finite, but as many as you want. And then let's say that they are connected. Let's say that they are connected for simplicity, but that's not a big deal. And then what happens is that there exists some moment on. So for each epsilon, there exists a moment that depends on this epsilon and this L, which is L is basically the maximal number of vertices that you can have here, the maximal number of vertices of each graph f of I. And then there is another constant that depends on this maximal number of vertices, such that if you do this, then up to an epsilon probability, from some point on, all this number of homomorphisms is concentrated. So it basically hits, asymptotically, it's hitting this number, the expected number. Yeah? So you have from some point on, I mean, you choose the epsilon, and then of course, depending on the epsilon, you have to go a bit further away. But you know, like, so in some sense, with high probability, you can say that this GNP actually converges to the expected number of homomorphisms when, very important, when you add a loop to every vertex. That's really important. Yeah? You add a loop at every vertex, and then you can converge it for every f. Because this is actually, so this is an and from some point on, yeah. So the whole thing, yeah, from some point on. N to the C is just this thing that goes to 0, so that basically kills you, and then you can say that the distance actually vanishes. So I mean, the C is a positive constant, and then you are basically like this distance from this to this actually goes to 0. I mean, not goes to 0, but it's a smaller power. It's a smaller power than this expected number. So the proportion will actually go to the proportion of, if you rearrange it, the proportion of this one divided by this one will go to basically the expected number of this. So basically, you need something here. You need something here that actually kills off this term that kind of goes to 0. Yeah. Okay, good. Yeah. So that's it.